This is Dr. Shargat Mulinger. In our previous video, we have discussed total internal reflection. These topics falls under the Unit 4 of Light and submodule 4.2 Refraction of Light. Learning objective is to identify the angle of incidence and the angle of refraction, also be able to relate the direction which light bends towards or away from the normal, if given the relative speed of light in the two medium. In total internal reflection, if we recapitulate the definition, we have stated it in our previous video as when light comes from denser medium towards the rarer medium, then the refracted ray bends away from the normal. For a certain angle of incidence, the refracted ray becomes 90 degree with the normal. This particular angle is known as critical angle. When light is falling on the denser medium more than the critical angle, instead of refraction, there will be only reflection from the surface between rarer and denser medium. This phenomenon is known as total internal reflection. So what happened? This is the incident ray, this one is glass. Glass means this is optically denser and air is optically rarer. So this light is falling the intermediate surface between air and glass. So some part of light will be refracted and some part of light is reflected from this plane. Now, if light is falling more than the critical angle, that is light is incidenting more than the critical angle, this is normal, more than the critical angle, then we will not get any refracted ray. That instead of refraction, only a refracted ray we will get. This phenomenon is known as, instead of refraction, only reflected ray we will get. This phenomenon is known as the total internal reflection. That means entire light is reflected here. At a small angle of incidence, the incident ray splits into refracted and reflected. This one is refracted, this one is reflected. When the angle, small angle of incidence, this, if you draw a normal in this direction, this is a small angle. So angle of refraction is less than 90 degree. If we draw the normal here, the angle of refraction is this, that is less than 90 degree. So angle of refraction is equal to angle of reflection is equal to angle of incidence. If we draw a normal here, then this is the angle of incidence, the angle of reflection. So angle of reflection is equal to angle of incidence. As the angle of incidence increases, the angle of refraction increases until. So if we draw the normal along this direction, so this is the angle of incidence. Now this angle of refraction is increases until angle of refraction is 90 degree. This is the normal, the angle of refraction becomes 90 degree, parallel to the surface of the medium. At this point, the angle of incidence is equal to critical angle. This is the critical angle. Already we have stated, when the angle of incidence is such that the refracted ray becomes 90 degree with the normal, then this is known as the critical angle. So angle of incidence is equal to C means critical angle when angle of refraction is 90 degree. As the angle of incidence increase beyond the critical angle, if we draw the normal, then this angle is the critical angle. More than the critical angle is the angle for which the refracted ray becomes 90 degree with the normal. So as the angle of incidence increase beyond the critical angle, that is greater than C, there is no more refracted ray. Here there is no refracted ray, only the reflected ray. All emergent rays are totally reflected inside the medium. This is known as total internal reflection or TIR. This is the picture. So conditions for TIR and critical angle: light is traveling slower in the first medium than in the second medium. That means this is the first medium, this is the second medium here in this case. So as the light is coming from denser to rarer, so denser is the first medium, rarer is the second medium. So light is traveling slower in the first medium, means denser medium, than in the second medium, that is rarer medium. So V1 is less than V2. Here we are considering velocity is V1, in air we are considering velocity is V2. So V2 is more than V1. Thus, light is moving from medium of higher refractive index to one of lower refractive index. Suppose this is the glass. Its refractive index is more than the refractive index of air. So the light, as we know, the refractive index means velocity of light in vacuum by velocity of light in medium. So air, in its case, the refractive index is 1, as we are considering vacuum and air is almost same. So it is equal to 1. But glass, velocity of light in vacuum is more than the velocity of light in vacuum. So it is more than 1. This one is more than 1. Here it is 1. So its refractive index is more than the refractive index of air. So thus light is moving from medium of higher refractive index. It is glass is the higher refractive index to one of lower refractive index, means air. So N1 is greater than N2. Here we are considering the glass, its refractive index is N1, and air, its refractive index is N2. Critical angle is defined when the angle of refraction is 90 degree to the normal. That means theta 2 is equal to 90 degree. So if we draw the normal in this direction, so for the angle of incidence, if we consider this angle is theta 2, so critical angle is the angle for which the refracted ray is 90 degree apart from the normal. So this angle is theta, this angle becomes theta 2 is equal to 90 degree. This is theta 2 is 9. If this is the direction of the refracted ray, then it will be the 90 degree. So critical angle, we are representing C and theta 2, that means the refracted angle is 90 degree. Total internal reflection occurs, or TIR occurs, when angle of incidence is larger than the critical angle. If we consider this angle is theta 1, then it should be more than the critical angle C. already we have discussed what is C. C is the angle of incidence for which the refracted ray becomes 90 degree. So theta 1 is the angle of incidence that is more than the critical angle for which total internal reflection will occur when light is coming from denser medium to the rarer medium. Calculating critical angle. So from this picture, this one is a refracted ray making an angle of theta 2. This is the incidence angle, this is theta 1. If C is equal to theta 1, then one picture, and this is the reflected ray and making an angle of smaller. So from Snell's law, another thing to remember, the glass, its refractive index is N1 and AR, its refractive index is N2. So from Snell's law, N1, it is making an angle of theta 1, the incidence ray. So sine of theta 1 is equal to N2, that means refractive index of AR into sine of theta 2. Critical angle C is equal to theta 1, thus solve for theta 1, N1 sine theta 1. Now for critical angle C is equal to theta 1 sine theta 2, that means this theta 2 becomes 90 degree. So sine 90 degree means 1. So we can write N1 sine theta 1 is equal to N2 sine 90 degree. So N1 sine theta 1 is equal to N2 as sine 90 degree is equal to 1. So at the critical angle, sine theta 1 is equal to N2 by N1. So theta 1 is equal to sine inverse N2 by N1. N2 is the refractive index of the rarer medium and N1 is the refractive index of the denser medium. If medium 2 is AR, already we have discussed this medium 2 here, already we have shown here AR, then N2 is equal to 1. So we can write theta 1 is equal to sine inverse 1 by N1 as N2 is equal to 1. So theta 1 is equal to C, C means critical angle. So C is equal to sine inverse 1 by N1. Always remember, in case of the rarer medium is AR, then the critical angle is equal to sine inverse 1 by N1. Now some data for total internal reflection, critical angles of different materials. If the medium is glass, its refractive index varies from 1.50 to 1.70 and the critical angle is 30 degree to 42 degree with respect to air. Water, its refractive index is 1.33 and critical angle is 49 degree. With respect to, definitely it's also air. That means rarer medium is air. Perspex, its refractive index is 1.5, critical angle is 42 degree. Diamond, its refractive index is 2.42, critical angle is 24 degree with respect to air. All are with respect to air. That means rarer medium is air and the denser mediums are glass, water, perspex, diamond, etc. Total internal reflection in diamonds. This is the picture, nice picture. The dazzling diamond, that means sparkling is shown here. The sparkling is due to number 1, cut of diamond faces. Number 2, high index of refraction, which means a very small critical angle. Here you can see diamond, its refractive index is 2.42 and critical angle is very small, 24 degree comparing others. So high index of refraction, which means a very small critical angle. Incident rays can undergo multiple total internal reflections inside a diamond before exiting the top of the diamond. So this is how, for this reason, due to the depending upon the cut of the diamond faces, we will get more sparkling, more the cuts, more the sparkles we will get from diamond if light falls onto it. What a picture. Total internal reflection in fiber optics cable. Technology that uses light to transmit information along glass cables. Fiber optics cable is made up of a bundle of glass fibers. These are the glass fibers. Bundles of glass fibers inside a fiber optic cable. Sample materials, high purity of glass and lucite. This is the picture we have taken from Bill Freimeyer. A nice picture of fiber optics. Fiber optic cable has a small critical angle, thus a very high refractive index. Light entering will always have a critical angle of incidence greater than the critical angle. Another picture of total internal reflection in fiber optics, we have taken it from eacademy.agnes.edu. Light does not escape as it travels along the fiber optics cable because it undergoes total internal reflection. This is how light is not coming out of the surface. It is not escaping from the cable. It is not escaping from the glass cable. So it is suffering total internal reflection inside the cable. So no light is coming out from this one. So loss of energy is very less. So courtesy is eacademy agnescott.edu of this picture. Total internal reflection in fiber optics cable. Picture A, it is showing us the cross-sectional view of a total fiber optic cable. Now, inner one is known as a core and outer one is known as a cladding. Inner material is more dense than the cladding, that is, core is denser than cladding. Now, when light is coming from core and falling on the surface of the cladding, then what is happening? It is denser, it is rarer. So more than the critical angle when light is falling or incidenting on the intermediate surface between the cladding and core, then it is suffering total internal reflection. So this is how in picture B it is showing light is passing through the cable without escaping from the cable, and it is flowing this path. So this is the optical fiber. Now here there is a picture. This is the glass. We know light always moves in straight line, but this is, suppose this is a bottle, it's a plastic bottle. There is a small hole and it is poured full of water. Now water is falling from this small piece of hole, and if light is given in same straight line of the hole in backward direction, it looks like the light, just like the light is falling in the bucket. The light is falling in the bucket. It is the actually Tyndall effect. The light is bending here. The light is bending. The same principle is following here in optical fiber. So it follows the principle of total internal reflection. Anybody, you can do this experiment at your home by using a torchlight or a small laser torch. You can keep the bottle on table and small bucket. Then you can see this experiment. It is a very easy experiment of Tyndall effect and the bending of light. Total internal reflections in fiber optics. The advantages of fiber optics are signals are not affected by electrical storms. Cable is smaller and lighter than copper cable. More signals can be carried over longer distances. So this is the picture I have taken from marylandcolonoscopy.com. So this is a fiber optics in endoscope medical treatment. This is the use. An endoscope is a flexible fiber cable through which internal cavities can be viewed. Routinely used in diagnosis of cancers and ulcers. So cable is passed for endoscopy and through the esophagus to our stomach, and the pictures are taken and can be viewed by the monitor. These are the pictures of different medical diagnoses. Endoscopy examination of a stomach. Endoscope inserted through the patient's mouth and fed down through throat. Image obtained by endoscope is projected onto a screen. A surgical instrument for obtaining a biopsy has been fed through the endoscope cable and controlled by the doctor. This is the picture doctor can see in the monitor. This is the digestive endoscopy. This picture is taken from Science Photo Library. Diagnosis of cancer. Doctors using a fibroscope to investigate suspected lung cancer in a patient's bronchi. A fibroscope is a flexible fiber optic cable with a camera on the end, similar to an endoscope.